Hi, welcome back to Physics Teacher. This is a question involving pendulums and collisions from a Sir Isaac Newton contest, which is a high school physics contest from Waterloo University. Give it a try and I'll be right back with the solution. Okay, so in this question we have two spheres. One is twice the mass of the other one, and this large sphere is lifted up to an angle of 60 degrees from the vertical, and then it's released so that it will swing down to come and hit this bottom sphere. When it hits the bottom sphere, it is perfectly to the vertical. And then what happens to the bottom sphere? It's going to go up, but the question is, to what angle from the vertical will it go up to? Or will that theta be greater than 90 degrees that it hits the ceiling? Alright, so we're going to analyze this in parts. First, this one is raised to a certain height. Let's call that height h. And so it has gravitational potential energy. And then as you let go, that gravitational potential energy converts into kinetic energy. So we're going to find the speed that it's going at just before it hits this sphere using energy conservation. Alright, so energy conservation, we have total energy before equals total energy after. So before, as we're raised here, we only have gravitational potential energy. And then as we fall to this lowest point, and the lowest point we'll set as a height of 0, we only have kinetic energy. So all gravitational potential energy gets converted into kinetic energy. Alright, so we need to figure out what that height is, because gravitational potential energy, the equation for it is mgh. And for kinetic energy, we have 1/2 mv squared. So what's this height? Well, let's analyze this triangle right here. This is a right angle triangle. And we can see if this length is L, this length here will be L cos 60 degrees. And that's just using our SOHCAHTOA or our trigonometric ratios. And what else do we know? We know that this entire length here is also L. So, put another way, L is h plus L cos 60. So if I rearrange to solve for h, then I can write h as L minus L cos 60. And that still equals 1/2 mv squared. And I can factor out an L, so this will be mgl times 1 minus cos 60 equals 1/2 mv squared. Okay, so we have a mass on both sides of this equation, so they are going to cancel. And what else do we have? 1 minus cos 60. Cos 60 is a half. And 1 minus a half is a half. And so therefore we have a half on both sides. So they cancel as well. Now just to make sure we don't get confused with masses, this was the mass of the large field sphere. That's the only one we're analyzing. I could have wrote 2m and have them cancel, or just a different m. Whatever that m is, it represents the mass of the large sphere, and it's going to cancel anyways. So we're just left with velocity squared equals gl. Okay, now moving on, it is going to hit, and it is going to hit in a completely elastic collision. So momentum is conserved, and we have no loss of energy, so kinetic energy will also be conserved. Let's start with momentum. So if we have momentum, it means conservation, total momentum before the collision equals total momentum after the collision. So before the collision, now because we're going to be using the mass of both spheres, I'm going to be very specific. This mass here, before the collision, has a certain momentum, mass times velocity. Its mass is 2m, and its velocity is v, the same v that we calculated here. Alright, and then we have the momentum after. Well, this one, the large sphere, it could certainly still be moving. We're not too sure. So we're going to have 2m, its mass, times some velocity, v. Now I should specify this v and this v is not the same. So let's call this v just v naught here, just so we don't get those confused. Then we need to add the momentum of our small sphere, which will be its mass times its velocity. And I'm going to call this Vs for the small one, right? Because these also must be different. Okay, now let's call this equation 1. And now let's look at conservation of kinetic energy since it is a completely elastic collision. Total kinetic energy before must equal total kinetic energy after. So before we have 1/2 mass, and this is the mass of the large sphere, so 2m, times v naught squared. And that's going to equal, again, 1/2 times the mass for the large sphere, times whatever its velocity is after the collision, so v squared, and then plus 1/2 m vs squared for the small sphere. Alright, so we can simplify this a bit. So 1/2 and the 2 cancel. Over here, again, 1/2 and the 2 cancel. And we have an m term in every single term, an m variable in every single term, so they're all going to cancel. And we are left with v naught squared equals v squared plus 1/2 vs squared. Now just to get rid of the half, if you like, we can multiply through by 2. So we have 2v naught squared equals 2v squared plus vs squared. So just remember, v naught is this initial speed right here of the large one. V is speed of the large one after the collision. And vs is the speed of the small one right after the collision. And let's call this equation 2. Alright, so making myself some room here, we're going to play a little bit with equation 2. So what I'm going to do is bring this term to the other side of the equation. So he'll have 2v naught squared minus 2v squared equals vs squared. And now I can factor out a 2, and you'll notice if we factor out a 2, we will have a difference of squares. So we can expand on that to write v naught minus v and v naught plus v all equals vs squared. And noticing from equation 1, what I can do is cancel out the mass terms, but also I'm going to bring this term to the other side of the equation and factor out a 2. So we'll have 2 times v naught minus v equals vs. So 2 times v naught minus v, that's right here. So I can substitute vs right into that equation there. So I will get vs times v naught plus v equals vs squared. So one of these will then cancel. And we are left with vs equals v naught plus v. So now I'm going to take this equation and I'm going to rearrange for v, which equals vs minus v naught. And now I can substitute this back in to equation 1 right here. So we have 2 times v naught is going to equal 2 times v, where v is vs minus v naught, plus vs. Alright, so let's expand. We have 2 vs minus 2 v naught plus vs. Collect like terms, so we have vs and vs, 3 vs. Bring this term to the other side, and that'll give us 4 v naught. So solving for vs then, we get vs equals 4/3 v naught. So what do we have here? Since we know that v naught, or v naught squared, is GL, we know that V naught, or Vs, is 4/3 times the root of GL. Alright, so what do we know then? We know that the velocity of the small sphere right after the collision is 4/3 root GL. And right after the collision, all that velocity is its kinetic energy, and that kinetic energy, as it goes up in its pendulum swing, is going to be converted back into gravitational energy. And once it reaches its maximum height, it'll all be gravitational energy. So to finish this problem, we're going to once again use conservation of energy. So the energy of the small sphere right after the collision equals the energy of the small sphere when it reaches maximum height. So the small sphere initially is all kinetic energy, and eventually it'll all be gravitational potential energy. Alright, so let's substitute. We know mass will cancel, and let's substitute for Vs squared, so that's going to be 4/3 times the root of GL, all squared, will equal GH. So here we have 1/2 times 16/9 times GL, which equals GH. Now that's a cool thing. Gravity is going to cancel, which means that wherever you did this experiment, if you did this experiment on the moon, you'd get the same result. Alright, and going back to what H is, well, we're going to do the same thing as before. If this is H, well, we can rearrange, you'll get the same equation. We can say H is L times 1 minus the cos of whatever this angle will be. It's not necessarily 60. So we'll say theta. Alright, and there's another cool thing, because our L's are also going to cancel. So we have 16/18, and our L's cancel. And now we can solve for theta. So the cos of theta is going to equal 1 minus 16/18, which is 2/18, or 1/9, and therefore theta equals 83.6 degrees, or